Okay, we're not doing that. All right, so this is a disaster of a day because we are only having 3 students here, and everybody is stressed out about the homework set for today, and so I don't think we're going to be able to make any progress forward, or at least maybe just a tiny bit. So, life is short, we'll make it work. All right, so folks were stressed about these ones that involve finding the equilibrium vector. All right, okay, so like, what problem? MJ was stressed about number 7. Were you stressed about 7? Were you stressed about 7? Okay. Problem 7 on page 468 gives you a transition matrix that's just 2 by 2, and it says find the equilibrium vector that will lead to. Let's first make sure we're all in agreement as to what that even means. What is the equilibrium vector?
It's that thing that makes it like all balance out at the end.
Right. No matter what, if it is a regular Markov chain, which these are, how do we know? Because there's no entries that are a 0, right? Not that necessarily every time that's the case, but whatever. If we know this one is a regular Markov chain, then regardless of what we started off with, whatever our initial probability vector was, you know, maybe that was 0.5, 0.5, like half was in one group and half was in another. We know that eventually we will get to a big V equilibrium vector. After a certain number of iterations or generations or whatever you want to say, as many links in your Markov chain as you've got, we will eventually get to some equilibrium. And that equilibrium vector does have the interesting property that V equals VP. Where, in other words, multiplying it by our probability, our transition matrix, which is given in the problem. That is what the problem is. Was it quarter, 3/4, half, half? Quarter, 3/4, half, half. It says you can solve this and come up with V. All right. Let's use our big brains in finite math. What's really going to be a better way of solving this? Isn't a better way of solving this really going to be about inverse matrices? Wouldn't it be, if we could divide by P over here, divide by P, wouldn't that be better? And then we could just, well, here's the deal. We're not learning about how to do that, because that's not quite right, until next time. So for now, we got to figure out a way to solve this way. And the book says we could set this up as a system of equations. I mean, if we called this thing, let's see here. This doesn't matter, right? No matter what this was, we're going to get to the same answer for V. So if we called this big V here, like if we called this V1, V2, and that's going to be equal to V1, V2 times that probability, that transition matrix, this sets up a system of equations, right? We could make it, you could say 1/4 V1 plus 1/2 V2 equals V1. And you could, let's do that. 1/4 V1 plus 3/4 V2 equals V1.
I thought that wasn't what you were, I thought you were supposed to do it where you took like the columns and...
Well, we're doing this. We're doing this part here. I mean, here's the deal. I'm only kind of drifting to the idea of what they're doing, okay? Hold on just a second.
Okay.
Similarly, let's do this other one. Let's see, that's that one. So this would be 3/4 V1 plus half. Is that right? Yeah. Would that be 3/4 V1 plus half V2? Did I do this one wrong before?
Yeah.
I did this one wrong. This should have been a half,
supposed to
shouldn't
be
it?
columns.
Was this right?
Yeah.
Okay. Do you see with some rearranging of this, we could then use Gauss-Jordan or elimination or substitution, and we could solve for V1 and V2. That's where they were going with this. But this gets complicated really fast. I mean, any more than 2 entries in this, it's going to start being a really big mess. I am not, and like I said, probably Wednesday, we're going to be learning that there's actually better ways we can do this anyway. So, I'm not so sold that you have to do this method of these inverses and so on. I'd actually rather if you had punted on this a little bit and tried to do this using a spreadsheet. So while that warms up,
I didn't even know that you did it on the spreadsheet.
well, sure.
Well, okay, so I started, but then I forgot how to do Gauss-Jordan.
That's okay.
And so
Or substitution or any of those, yeah.
like I was when I got hooked, it was on like the big ones in like 28, where it was like a 5 by 5. So
See, like, because like I stopped at partway through number 7, but like the point
I
that
didn't-
I got to, the matrix,
did
like
number 7.
the end matrix, like it was set up and it looked exactly like what it would say it was. It was just that I don't know if I messed up along the way because I'm not sure how to do this.
I figured
And
out
so
number
the
7.
numbers didn't
It
come out
did.
right.
Yes, there's a Gauss-Jordan calculator.
Cool. Good, cool, sorry.
Sorry,
I lost track. There were 2 stories going on at the same time. So you were what?
mine's not
So,
story, mine's just
I did the Gauss-Jordan method, and then like the end table that I got to, it was set up exactly to where it would be like it had 1, like in the top left and 1 right here, and then there were zeros at the bottom. But the problem was is that I think I messed up along the way because I don't know how to do this,
Sure.
and so it wasn't the answer that was in the back of the book, and nothing was helping. So
But
Well, let
obviously
me-
you can't use it, because she just said she used the Gauss-Jordan calculator.
Well, she got it to work, but that's okay. I mean, I'm happy. But let me just show you. I think here's the deal. I'm not loving this part that they. It's totally cool that it worked, right? On the other hand, it's not where we're going with this anyway, right? And so here's the deal. In the goals of the course are things like modeling and using spreadsheets to solve problems and stuff like that. So let me show you how we could have done this differently, okay? We could have just said that we're going to try it. So I put in my transition matrix P here. And let me make this a little bit bigger, just so that it's a little more likely they'll be able to see it. And I'm going to move over just a hair over here. Let's just put this over here. Okay. So I have made a transition matrix P here. And because it's going to be simpler, I'm going to show you my rock star trick of, I'm going to define this area, 2 by 2 here, as being a named range called P. So from here on out, if I use the symbol P, it will know I mean these cells right here. And I'm going to make a little original, what is this right called? A probability vector or whatever, the original population vector over here. And remember, it does not matter what we put in there, because we're going to go, it's going to drift towards, it's going to gravitate towards the equilibrium vector. So I'm going to start off with half the people in group 1 and half in group 2. But once again, I need to set that up as a named range, again, just because I know that this is going to be, how much of my day do I spend doing spreadsheets? I know that this is going to save us time. All right? All right, so like if I want p squared, I'm going to say I want m mult of p times p. All right? And I want, but I'm going to actually make this even simpler. I'm just going to call this 2, because that's the second one. And I'll say this is this one plus 1. That's going to be generation 3. That makes sense? All right. And that will be m mult these cells times p. And the reason why I did that is I can just copy this now. Oh, wait, went wrong. M mult that times p. What did I do wrong? Was it off by 1? Oh, I went off by 1. Never mind. Hold on. We'll just do it that way. Copy. Paste. See? 4, 5, 6, 7, 8, 9, 10. I now have, this is p to the 10th power. Because it is m mult of the 9th power times p. And it's and that's pretty slick. I got that done. And notice how the matrix isn't really changing very much anymore. Right? That's what we want to see, right? Is as you have more and more generations, the transition matrix gets to be more and more the same. Alright? And in each generation along the way, we have a new version of the distribution of those groups, which is the multiplication of x naught and the current probability matrix, not probability, transition matrix. So like after one generation, now this much of the group is in group 1 and this much of the group is in group 2. And once I've done that, I can just keep pasting that in. for each of the generations. And look, I think, can we agree that we're gravitating towards 0.4, 0.6? Now, what is the answer to the back of the book for question 7?
2/5 and 3/5.
2/5 and 3/5? How about that? Is that what you got by Gaussian elimination? Yeah, it works. Okay? So we model, instead of actually doing all this math, because here's the deal. You could have done this, Malia got it to work using Gaussian elimination.
I messed
The
up.
computer
along
got
the
it to
way.
work.
You what?
I messed up along.
You just messed up along the way. But you know what? This would have gotten much harder to do using Gaussian elimination if we had 3 variables. And it would have gotten even harder if we had 4. Right? If there were 4 states, if there was a group 1, group 2, group 3, and group 4, we only even did, that would be a system of 4 equations with 4 variables. We only even did 1 or 2 problems that hard back in the section where we did the systems of linear equations or whatever. So this would suddenly, but this would have been no harder with 4 rows and 4 columns. I just would have been copying and pasting a bigger area. So this would have, and what if it had been 10 rows and 10 columns? It would not have gotten any harder, right? So this actually is a pretty slick way to be solving these kinds of problems. Let's do,
Can we do one of the word problems?
yes. So here's the deal. I'm going to be making something here, and we're going to call this page, how about we call this section 10.2 homework. And you know what I'm going to do eventually is I'll share this with you guys. So let's rename this page here, was this problem 7?
Yeah.
Okay. And then let's do another one. And we can do it, we have as much time as we want, right? Because it's just the 4 of us. And so, alright. So what do we got going on? Which one do you want to do as a story problem?
Both. All of them.
I honestly don't remember what the assignment
On
was.
28 and 29.
There's
Yeah.
only 3 of them.
Especially 28. That one was the scariest.
It looks the scariest.
I would much rather.
And
that
then
one.
29, because that was not good for me.
Okay.
Maybe 29. I don't want
I didn't even start because I was like, I don't even know what I'm doing for
All right.
number 7. So
Yeah. Why would I
don't
know what to do?
All right.
Yeah, exactly. It's like it's just gonna be
All right.
worse.
How about we do 29 first because it's an odd number?
Okay.
And we can compare the answer in the back of the book. Okay? I have to admit I have not made a key for this assignment yet because, you know, life is keeps intervening. Alright, so in problem 29 on page 469 it says business. As we saw in the last section, the change in the size of businesses in a certain Canadian city from one year to the next could be described by a Markov chain. The businesses were described in 3 categories based on size: small, medium, and large. And the transition period for one is given in the next column. So here's their transition matrix about moving from being a small to a medium to a large business. If these trends continue, in the long run, what percent of the businesses will be small, medium, or large? Okay, we could do this like what's behind the screen here, right? We could make this a system of equations by Gaussian elimination, right? Big V equals big V times P. Let's actually at least look at it. Okay, so they gave us some transition matrix. I don't want to write it all out because it's weird numbers, right? They're not like fractions or something, they're weird. They're all weird. But we haven't. It's that big thing. It's a 3 by 3 big thing right here. And we know that what we're trying to solve for is big V, the equilibrium vector. Because that's what they mean by in the long run. In the long run, over a series of years, how will they break down into those 3 categories? And we know that it has the property V equals V times P. So again, okay, we know that this V is really V1, V2, V3. Where that is the fraction of them that are in small, medium, and large businesses. Okay, once again, we could then write this out as a matrix equation. I'll just write P. And we would have to write all this out. V1 times whatever this is, plus V2 times this, plus V3 times this, equals V1. V1 times this, plus V2 times this, plus V3 times this, equals V2. V1 plus this plus V2 times this times V3 times this equals V3. We could have a system of 3 equations and 3 unknowns with awkward numbers, but we could do it. Okay? It would be messy, but it could be done. And then it would be a system of 3 equations and 3 unknowns, which is very error prone, but it could be done. Or, again, since it's buried in the goals of the class that we do more of these kind of things in modeling and so on, let's actually model it. So I'm going to call this, what is this, problem 29? There we go. I'm going to rename the spreadsheet. Problem 29. Okay. So, we have a probability matrix here. I'm sorry, not probability, a transition matrix called P. And it says 0.9216, 0.0780, 0.0004, 0.046, 0.8959, and 0.0581, and 0.0003, and 0.0301, and 0.9696. Now, with weird numbers like this, just to convince myself things are okay, remember one of the properties of a transition matrix is each of the rows that are add up to 1. And I'm just going to check that real quick. Yes, it does. Okay, because it would have been so easy to turn some numbers around or something. All right. Notice, by the way, that the numbers on the diagonal are quite close to 1. If the numbers on the diagonal are quite close to 1, that means that you're very likely to stay in the group you are, right? I mean, this is that you're a large business, and a year from now you'll still be a large business. This is you're a small business, and a year from now you'll still be a small business. Okay. If those numbers were actually 1, we'd have an absorbing matrix, but you're not going to learn that until next time. Because that contracted. If one of those entries was a 1, you have no choice, right? Okay. We know we want to have this matrix here, and we want to call this P. Now, Google Spreadsheet actually hates it if you have 2 ranges called the same thing, so I have to actually be a little bit awkward here. Let's call this one, instead of calling it P, let's call it P. Okay, I'm sorry, you have to do what you gotta do, okay? Alright, so we got something called P. Alright, so this will be P squared equals matrix multiplication, P times P. Alright, and the third generation, which is 1 plus the previous generation, is just M mult of the previous generation times P. Alright, let's take that out as many generations as we damn well please. 1/4, the 5th, the 6th, the 7th, the 8th, the 9th, the 10th. I'm actually going to take it farther, because as I'm looking here, the matrix is still changing a bit from one generation to another. Remember, eventually a transition matrix should be basically the same one generation after another too. Let's just keep going farther and farther with this, because we see this still be changing. And hey, it's just copying and pasting. It's not like I'm working all that hard on this. We're to the 25th generation already.
I got short into work with this.
You did?
Yeah.
Hold on.
I feel like I should be the sponsor to this Gauss Jordan calculator.
Start yourself a YouTube
All right.
channel.
I am not understanding why we're not slowing down here. Hold on. Where's all this going? 45 years later, we're still drifting. That's interesting.
And that's the summary of Star Trek Voyager.
That's true. Where's everybody ending up in this one? There we go. At least we're slowing down now.
Everyone's going into big business.
Goodness gracious. Yes, they're all drifting. I wonder if that's true.
Probably not. If anything.
Okay, well we're only changing by less than 1% each time now. Alright, so I'm going to go out to 70 years, because that's definitely what we want, right? Alright, we went out to 70 years here. I'm deliberately making kind of an obtuse thing here. Okay. Alright. Interesting. Alright, X naught. It should not matter how we started off. So what the heck? I'll make 4/10 of the businesses small, 4/10 big, middle, and 2/10 big. It should not matter. Alright, we got to give that a named range here for the way this is going to be easiest. So I'm going to name it, and let's see, we've already got that, so let's call that X0. Alright, because we already had an X naught. Alright, so after one generation, it's going to be matrix multiplication of X0 and this transition matrix. And alright, and once I have that, I should be able to do that for the second, third, fourth, fifth, sixth, seventh, eighth. I don't actually know if I can copy this down at a bunch at a time. I think I could. Let's just do 3 at a time. Boom. Yay. Boom.
Problem solved. Improvise, adapt, overcome.
So we're still having fewer and fewer small businesses. That's really interesting, actually. All right, keeping moving here. Let's just
We're
keep
gonna have
going.
to go pretty far.
Do I?
I think, like, the small it will end up being like 16%.
Okay. Well, we're getting there.
45 minutes.
All right. Did you get the answer in the back of the book?
Yeah, it's 16.9
All right.
for small.
We're just simulating distant values. Oh, we got all the way out there. Okay, so I got it as far as 17.4. We could keep going more and more generations.
We can
So,
see it though.
but you can see the pattern here, right? Okay, all the way out to 70 generations, 70 years in the future. All right, so the answer I got is 17.4% are small businesses. And you said what, 16.9?
Yeah.
And 28.8% are medium-sized businesses. What did you get?
28.47.
28%. I'm only off by a few tenths of a percent. I mean, I'm good, right? Do you think these predictions are really all that good 70 years in the future? Right? Obviously, things will have changed, right? And I got 53.8% are large businesses. What'd you have?
54.6.
Okay. By the way, we could have gotten this better. We could have ended up with better numbers if we had started closer to what the answer actually was, right? If we had started off with closer to what the actual answer was, and I didn't have to change so many, we would have gotten after 70 years even closer to your answer. See, look at what I got now after 70 years. Right? I had kind of unrealistic assumptions on how we started off, right? If I had started off at something, what if they were all small businesses when we started? Okay? Over the course of 70 years, we still get pretty damn close to your numbers, right? It's just 70 years wasn't enough to get rid of all those small businesses.
Okay, so it's just a matter of, how many iterations does it take?
Yeah.
Okay.
So, alright. That's cool. That's a cool problem. Alright, now we will bravely go forth and look at an even-numbered problem. How about 28? Mortgage refinancing. Hey, yesterday in quantitative reasoning, we were learning about mortgages and amortized loans. And we wondered what the hell that word meant, and because MJ's here, she always loves such things. I do know what it is. Amortized comes from amortir, a Middle French word that means to slowly kill off. Because when you amortize an installment loan, you're slowly killing off the original amount you owe. Mortgage does come from mort, death. It's like death, resolved by death, or something like that, because you're presuming that you will not actually pay it off, and it is resolved by your death.
I mean, yeah, where's the one there? But
Cool. I had no idea. It was a useful thing to learn. 28. Mortgage. Once you know that, though, about the history of the word mortgage, will you ever forget to put the T in there again? Most people, when they write the word mortgage, don't remember.
That's how I remembered it. Was I read it as like death and engage, So like gauging death.
No, it's actually a gauge. Actually,
Right,
is
no,
a stem
I
that
do-
meant like
Yeah.
resolved by or something.
Right,
Like that,
but you know what I mean, and so
Yeah.
that's why I was like, okay, well that makes sense.
yeah. It makes
to me.
perfectly good sense. Do
Gauge
you know what the word
sense.
adult means?
What?
Do you know what the word adult means? It's actually an
Sad.
acronym.
What is it?
Accumulator of debt until life terminates. That's why it, yeah. No, I told them that. They looked at me with this dead look in their eyes. Anyway, alright, moving on, mortgages.
I'm not okay now.
What?
I said I'm not okay now.
It was not a good date because Jalen's car died and she thinks she needs a new car and she was going to go try to get a car loan and stuff like that. And I'm like, oh, lady,
Honey, no.
this is a good day to not be talking about that because we're doing loans.
Sweet honey child.
Alright, in 2009, many homeowners refinanced their mortgages to take advantage of the new lower interest rates. Yes, nothing like the economy collapsing to think, yeah, let's refinance. Most of the mortgages could be classified into 4 groups: adjustable rate, 15-year rate, 20-year fixed rate, and 30-year fixed rate. We're going to be doing that. Okay. Sometimes when a homeowner refinanced, the new loan was the same type as the old loan, and sometimes it was different. The breakdown in the percent in decimal form of each category is shown below. If these conversion rates were to persist, find the long-range trend for the percent of loans of each type. Source is Freddie Mac. Okay, let us make a new page, which we will call problem 28. Alright, so we have these loans, and we have a matrix. See, like they had an adjustable rate and they kept an adjustable rate. They had a 15-year rate and they changed to an adjustable rate. Alright, notice. How many people liked those adjustable rate mortgages? If you had an adjustable rate mortgage, did you keep an adjustable rate mortgage? No, only 4% of people did. Do you know why? Because mortgage rates were ridiculously low after the economy fell apart, right? Why would you choose an adjustable rate where it could change from year to year?
Because you like paying more.
Because you're like, I want to give more money to the bank. No, of course, nobody did it. Notice how people who had 30-year loans, nobody chose the adjustable one. If you're going to be paying for 30 years, you want to be paying 30 years at the lowest rate, right?
So what exactly happened in 2008?
The housing bubble burst and banks went.
No, I know that part, but like, what happened? Like, what caused that? Because like it did.
Banks were selling each
life.
other mortgages.
Oh.
Here's the deal. The way it normally works is the bank only takes a chance on you and lends you the money if they're pretty sure you'll pay it back. But banks figured out in the mid-2000s that there was a better way to make money. Make the loan to anybody and everybody and then sell the loan to somebody else. So they would put together the group, and they'd package up 2,000 loans for coming together to $20 million and sell it as a product. An investor could buy those 2,000 loans and they'd make all that money off of you for the next 20, 30 years as you're paying off that mortgage, right? As an investor, that looked like a pretty big deal until you realize something. Banks were loaning to anybody, regardless of their credit history, regardless of their ability to pay, and because then it wasn't the bank's problem, they sold it to somebody else, right?
That sounds like what happened leading up to the Great Depression.
Yeah, in some ways. So yeah, once it all fell apart and people realized nobody was going to be paying these loans back, then the economy fell apart. And nobody was willing to, that's why nobody would borrow. That's why the interest rates were low, but nobody could borrow because banks were scared to death, right? Because there were all these crap loans out there, right? Anyway, so yes, that's what happened. All right, so let's work on the actual problem itself. 0.04, 0.22, 0.07, 0.67. This could be done. And in this chapter, they actually assumed you were going to be doing it using Gaussian elimination and all that kind of stuff. And Malia wants to actually make commercials for her Gaussian elimination calculator or whatever. Is that the one it is? I can't remember.
I don't know, yeah.
She was going to do this. But we're going to do it by modeling. We're going to model the solution here. Hey, I'm noticing that there's some zeros in here. Wait a minute. If there's some zeros in here, is this a regular matrix? Is this a regular Markov chain? I'm going to check, by the way, to make sure that these all add up to 1, just because I'm always scared of that. Well, it might be. What do you have to be a regular Markov chain?
It has to, the zeros have to change.
Yeah, you have to have some generation of the transition matrix where there's no longer any zeros. Okay? Just because at this generation there is a 0, that actually doesn't necessarily mean the end of the world. Okay, now we need to make this a named range for this to be not such a big deal. So let's make this a named range. Let's call it P like the vegetable this time. Okay. So our second generation will be M mult P times P. Notice, by the way, by the second generation already, none of them are zeros.
That's generally what happens, though, isn't it?
Well, who's going to finance the reform? Well, okay, so what does this mean? This is talking about people who've refinanced twice, right?
Right.
So you've refinanced and then refinanced again, okay? So already by then, every product, somebody's in, right? We no longer have subcategories where like nobody had refinanced into category, whatever one was, adjustable rates, all right? Equals, so then we get the third generation here, equals matrix multiplication of the previous generation's transition matrix times P, all right? And I'll just take this out to 10. I mean, who's going to refinance more than 10 times? Good grief. Who's going to refinance twice? Some people did twice.
I can see up to like 3 times.
It just depends. I mean, there's actually help from a banker. In practice, you don't really refinance too many times because every time you refinance, there's costs about that. Effectively, you have to pay the bank for doing all that paperwork and stuff like that, right? At some point, the amount of money you're saving by getting a slightly better interest rate or something like that when you refinanced doesn't cover the cost of what you had to pay for the bank. There might be $1,000 in paperwork costs and stuff like that. And so at some point, you're not saving enough money to make it worth your work. All right. All right, then we have to start off with some breakdown of people who were in each of these groups. Let's see, and we don't have any guidance on that because it doesn't, in theory, matter. So for lack of a better idea, I'm just going to go ahead and make each of the 4 groups have a quarter of the people. And I need to name this little range here.
Or X naught.
Sure, how about X naught?
That's not what I was thinking.
Okay. All right. So now, at the first generation, we would have M mult of X naught times its transition matrix right here. And now practically nobody has a variable rate interest rate. More people have 15-year, 20-year. 20-year actually went down. That's interesting. But 30-year went way up. Which makes sense, right? Because, I mean, the 30-year was the best deal, right? I mean, 30 years, if interest rates by 2009, the Obama administration had to lower interest rates near 0. Interest rates were lower than inflation. It was cheaper to borrow money than to pay it. All right, it makes sense. Lock into those rates now. All right, so let's do 10 generations. You've refinanced up to 10 times. Boy, nobody's liking those variable rate interest rates in column 1, that's for sure. By the 10th iteration, we're getting pretty close to a solution here. Notice that there's very little difference between the 9th iteration and the 10th iteration. Notice there's virtually no difference here. I mean, it's out to the hundredths of 1%. Okay, so what we know is about 59% of the people decided to go for a 30-year interest rate. 43% went for a 20-year. 36.5% went for a 15-year, and basically nobody went for a variable rate after a refinancing or 2, which of course makes sense, right? If the rates were super duper low when they came up with this table over here, it made no sense of this transition matrix. It would make no sense for you to take a variable rate when realistically the rates were only going to go up. Cool. I like these problems, but I don't like the Gaussian elimination thing. Did you do it using your Gaussian elimination calculator? Did you get roughly the same answer?
For the X1, I got 0.0000, okay, 0.000449.
Okay, so
They
she's
give
only
it to me in
different. The
fraction
7, she's
form.
got a 9.
They give it to me in fraction form, so
Okay.
1,050,37 divided by
They give it to you in fractions?
8,037. Then I got 36.46, like 47.
Okay, so she got a 4 instead of a 5 in this place.
And then,
All right, the point is she's
and
got
then
the same
I got
answer.
close.
Close enough, right?
Yeah.
All right. Excellent. Hey, so the whole point of this game was to do multiple refinancings using this matrix right here as the transition. But here's the deal, that matrix would change all the time, right? I mean, in practice, the only reason you would refinance a second time is if interest rates had changed again, right? So, I mean, but if interest rates change again, the groups of people moving from one group to another would change, right? So in practice, this is kind of a stupid problem. Again, I don't like these Markov chain problems as well when they're like economics or voting or social groups because they don't really work. It's better when they're like a physical system, right? But that's not the kind of problems they seem to in general be choosing. I mean, notice that the rest seem to be, oh, weather, 38. Weather on a certain spot is classified as fair, cloudy, without rain, or rainy. I don't really like that problem for meteorological reasons. Do you need more time to solve this problem set? I bet you do, and I bet Andrew and Lisa and Luke and Sierra all do too. So, I vote we don't go and do anything other than finish this.
Seconded.
Okay, especially since, I mean, good grief, it's just the weekend before Monday. Alright. Because where we're going with this, while fun, oh, I don't even have it done, is the next section, which is going to take us a couple days to get through, which are absorbing Markov chains.
Which wouldn't you rather have everyone there and everyone understanding for that?
MJ's being very manipulative
No,
today, our friends.
I'm not meaning that in like a weird, ridiculous,
I
or
know.
sarcastic way. I'm just meaning, wouldn't that be better for everyone?
It would be.
Thank you.
So here's the deal.
To the group.
Just so that we're like turning our wheels thinking. An absorbing Markov chain is one where there's entries that have zeros and there's ones and there's zeros. Where once you get to a particular state, you can't get away. And the classic example would be things like gambling. Where one of the, you know, like if the different states are how much money you have. Alright? You've got, let's say there's some game you're playing, you have $10, every time you play it costs $1, and you get $1 or $2. You know, you'll either lose the $1 or get it out. But one of the ways you can, what happens when you get to $0? You're stuck, right? You can't get out of the state of being. There's no way you can get out of having, no matter whether you're in class 1, class 2, or class 3, there was always a way to get to the other two classes. But once you're stuck at having zero money, Vegas is not going to say, oh, go give that wheel a spin one more time. You might get yourself $1. No, once you have $0, that's called gambler's ruin. You're done now, right? There are all kinds of these problems where when you get to a certain state, you can't get out. Those are going to be absorbing Markov chains, where you could change, oh, now you're here. What if once you became poor, there was no way of becoming out of poor? Right? You could go from class 2 to class 3 and class 3 to class 2, but to get to class 1, there was no way out. Some people would say that is how it works, right? Once you were going to Lisa's dry cleaner and you were going to Malia's dry cleaner and bouncing back and forth, but once you tried MJ's dry cleaner, you never went back, right? You were always at MJ's dry cleaner after that, okay?
Always, never went home.
You never, right?
I had to start subletting.
Yeah, so that's what we're going to be doing with Markov chains. Chains where now something different can happen. But when you get to one of the states, now you're there forever. Okay? That's where we're going to go. All right, I vote because it is a weird day. Let's take a break, and I will call that a day, and I will start figuring out what the hell we're going to do about pre-calc since we have no room and we have like a third of the students missing, both of which are sub-ideal.
And we can't just go out to